Alrighty, thank you everybody for coming to our Lunch and Learn today, March 4th, right? Yeah. So this week we're very fortunate to have the SEG Distinguished Lecturer for 2021, Dr. David Cooke. David is the Director for CODES, the Center for Ore Deposit and Earth Sciences at the University of Tasmania. David and his research team have been investigating porphyry and epithermal systems for over 3 decades, investigating genetic aspects, characterizing deposits, and of course, developing new innovative geochemical and geological exploration tools to aid discovery. David is also the editor of, an associate editor of economic geology, recipient of the Haddon Forrester King Medal from the Australian Academy of Sciences in 2018, the SEG Silver Medal in 2013, and the Thayer Lindsley Distinguished Lecturer Award in 2005. And like I said, he is the Distinguished Lecturer for SEG this year. And so thank you, David, for agreeing to give this talk, and take it away.
Thank you very much, Caleb, and thank you for inviting me to give this presentation. It's always a great pleasure to have the opportunity to talk to the folks at Colorado School of Mines. I wish I was there in person, but in the world we live in, this is how we're communicating today. And I do have to say it is actually an effective way of reaching out all around the world. So thank you very much for coming along. What I'm going to share with you today is some of the learnings we've been getting from an intensive research program into the distal footprints of hydrothermal alteration that occurs around porphyry, copper and gold deposits. So I'm going to try to illustrate with a few examples how we can extend the geochemical footprint of these deposits by analysing alteration minerals rather than by using bulk rock chemistry, and what some of the surprising outcomes can be of going into this space and how it can be advantageous to add this to the explorer's toolbox. Before I do that, I'd just like to give a little plug for the Society. As the SEG Distinguished Lecturer, I'm sure that those of you at Colorado School of Mines are all very well aware of the benefits of being part of the Society, but there are particularly huge benefits for students to join the Society because of all of the professional development opportunities, the conference opportunities, the field trips that they provide through the student chapter program and the like. You're getting benefits of networking with industry professionals and academics, access to the journals, publications, Economic Geology and the Discovery newsletter. So if you are not currently a member of the Society, I'd be very happy if you want to reach out to me and ask more about being a member of the Society. And if you're looking at being sponsored to join, they're absolutely very happy to help out in that regard. One of the benefits of the Society is that they do provide access to the SEG travelling lecturers, and in 2021 there are 3 excellent lecturers that you can see here, and me as well, and you can reach out to all of these people and see if they will be available to talk to your student chapter. So this is part of the program of disseminating information that's of relevance to our community in economic geology. So what I would like to share with you today is these outcomes that we've been working on with regard to porphyry systems. But to begin, I thought we should touch on a few basic elements of porphyry, copper, gold and molybdenum deposits that inform the discussion that is going to follow on as we progress through the talk. So here is a classic diagram from Dick Silito's seminal paper back in 2010, which shows alteration domains around a porphyry deposit. So porphyry deposits share a number of common elements. Even though they're variable in detail when you look from deposit to deposit, there are a few key features that are what bind the porphyry family together, and there are some key features that are extremely useful to guide exploration for these major resources of copper, gold and molybdenum. To start with, we have mineralisation and alteration forming in and around a multi-phase intrusive complex. And in Dick's cartoon, that intrusive complex is shown down at the bottom of the cartoon with the plus symbols. So these multi-phase intrusions have a porphyritic texture due to their crystallization history, early slow cooling followed by very rapid quenching of the ground mass as hydrothermal fluids are released from the intrusions. So the process of releasing fluids creates that porphyritic texture, and that's why we call them porphyry deposits. The magmas that produce porphyry deposits are typically oxidized, so that means that they are capable of carrying significant amounts of copper, gold, molybdenum and sulfur in an oxidized form from the domain of partial melting down in the mantle all the way up to the upper crust. And they may be in place, the final tips of these intrusive complexes at depths of between about 4 and 1 kilometres below the surface. They typically form in convergent margin settings, so they are a signature ore deposit type of oceanic island arc and continental arc settings. Some porphyry deposits form in more complicated tectonic settings, post-subduction environments and in collisional zones as well. Porphyry deposits' signature feature in their mineralised body is a very intensely developed vein stockwork where we see multiple generations of quartz sulfide veins that cross-cut and overprint each other. And in some cases, we see significant bodies of hydrothermal breccia hosting mineralisation as well. When we are exploring for these deposits, we need to understand the alteration distribution within and around them, because ultimately the alteration footprint of the deposit extends far greater than the actual ore zone. And so when navigating from distal regions into the deposit centre, we're needing to work through subtle transformations in alteration minerals in the country rocks to guide us to the ore zone. And Dick's cartoon shows you some of the key alteration types we see in porphyry deposits. These vary as a function of protolith, these vary as a function of fluid evolution and the batches of fluids being released from different intrusions and how they overprint each other. So we get a complicated sequence of both overprinting and zoning, and we may get telescoping, the collapse of very shallow level alteration systems into early formed deep level alteration systems due to landscape degradation during porphyry formation. So classic porphyry models have a potassic core surrounded by a halo of propylitic alteration. And this is particularly common in volcanic hosted porphyry systems. And the idea is that the propylitic halo is the distal equivalent of that potassic core. So they form at the same time. There is also overprinting clay and white microalteration, and we can see here what Dick is labelling as chlorite, sericite, cericitic, quartz porphyllite, quartz alunite, etc. These tend to form late, and their distribution varies from deposit to deposit, sometimes very strongly fault controlled, sometimes extensive and pervasive, sometimes separated from the potassic zone by more than 1 kilometre vertically, and sometimes superimposed right into the core of the deposit. What happens with this alteration, though, is ultimately we are going to generate zonation patterns. Zonation of alteration, zonation of sulfides, and zonation of metal. And these zonation patterns are what we are trying to use to guide us to the mineralised centre. Now, we've known about metal zoning around intrusive complexes for many years. Emmons published a seminal paper back in 1927 highlighting from the study of looking at mineral deposits around granitoids that some metals form within and close to the intrusive complex. Metals such as gold, silver, copper, iron, tin, tungsten tend to be proximal, and other metals can be dispersed significant distances from the granitoid. I've just lost my screen. Are you still seeing the screen?
Yeah, we can still see your screen.
Oh, that's interesting. I don't know why. I just lost the screen for a minute. Sorry. Hopefully it will come back. Anyway, I can keep talking while it's working its way through. So this distal versus proximal pathfinder metal tells us something about metal solubilities in the hydrothermal fluid. The intrusions are carrying the metals and releasing them as they exsolve fluids, and the metals are precipitating out based on solubility relationships. The least soluble metals precipitate first from the highest temperature, high salinity fluids. The more volatile elements are dispersed considerable distances and precipitate out at low pressures from low salinity fluids. Now, Scott Halley and the Footprints team at MDRU published a beautiful paper in the SEG newsletter back in 2015 that gave us some lovely quantification of geochemical anomalies within and around an intrusive complex. And this cartoon that we're looking at here is really based on the Ann Mason porphyry copper molybdenum system in Yerington in Nevada, where the system is tilted. So there's an excellent vertical profile through the deposit. And so we can see the architecture of the Yerington system and its geochemical anomaly going above it. And what I want you to look at there is not so much the thresholds of pathfinder elements that can be detected by modern high-quality whole rock geochemistry. What I want you to look at is the dimensions of that footprint. What Scott's showing is that there's a plume of alteration that's going up 3 or 4 kilometres above the porphyry deposit towards the paleo surface with geochemical anomalism, and we're getting a plume of that geochemical anomalism spreading out laterally from the Ann Mason porphyry at depth, where the halo is about 1 kilometre, going up to a very broad plume in what is a lithocap above the deposit, extending for 4 kilometres or more. So let's try to look at that type of thing in plan view and just try to explain what our research team, our collaboration has been doing over the years to try to expand the exploration geochemical footprint of a porphyry deposit. So this is a Google Earth image of the southwest corner of the island of Sumbawa in Indonesia, and you are looking at the Batu Hijau open pit. So Batu Hijau is a giant porphyry copper gold deposit, about 1.6 billion tonnes at about 0.4 copper and 0.4 gold, and it's in the jungle on the equator, and it's at a deep erosion level. So this deposit has a core of potassic alteration with strong biotite and magnetite, passing outwards to a halo of propylitic alteration defined by epidote and chlorite and calcite and a bit of actinolite. And we'll look at a geological map of that in a minute. But what I just wanted to highlight for you is the different types of footprints we might use to find this deposit. So we use geophysics, geochemistry, and geology. And with geophysics, because porphyry deposits can have a magnetite-rich core, as Batu Hijau does, if you are at the right erosion level and there is no significant alteration over printing of magnetite-destructive alteration, sometimes magnetics is a direct detection mechanism. So here we have a bullseye target in the centre of what is now the Batu Hijau open pit. So the image on the right is showing you the aeromag result for Batu Hijau, and we have that very strong magnetic anomaly associated with the magnetite veins and alteration in the core of the deposit. A second magnetic anomaly associated with some magnetite-bearing skarn on the southwest side of the porphyry. Another geophysical footprint is provided by pyrite. Porphyry deposits typically have a pyrite halo that extends for 1 to 2 kilometres out from the porphyry centre. And so IP surveys can typically pick up a chargeability high around the porphyry deposit. Here you can see a lovely ring around the Batu Hijau system, giving us that chargeability anomaly. A second chargeability anomaly in the core of this deposit because the chalcopyrite magnetite is actually giving a response as well. But that's giving you a geophysical footprint of about 2 kilometres that's helping to tell you where Batu Hijau is located. If we did whole rock sampling and we were applying all the pathfinders that Scott Halley was outlining, basically that rock geochemistry generally is picking up where the rock is containing sulfides. So we're getting a similar sort of geochemical dispersion halo in the bedrock sampling. I'm not talking here about transported media such as stream sediments or till, but the rock geochemistry footprint will give you a similar geochemical anomaly to the IP footprint or similar dimensions. You might be able to extend that with, if you're lucky or if you're really working hard on the low level anomalism in the rock. So our team has been taking those rocks and trying to deconstruct them and look at the individual minerals to see if the geochemical anomalism is carried further out by fluids out from the porphyry centre. So rather than analysing the bulk rock, we analyse specific alteration minerals. And what we're finding is that this allows us to detect geochemical anomalism in bedrock samples up to, in some cases, greater than 5 kilometres from the centre of the deposit. So a significant expansion in the search radius where geochemistry can detect the presence of a porphyry system. So here is a cartoon we put out a number of years ago that's sort of trying to show the two main exploration domains you might contend with in a porphyry system: the green rock environment and the lithocap environment. And Zhao Shan would have talked to you, I'm sure, about lithocaps quite extensively. That's not what I'm talking about today, but that's a very important exploration domain that is really challenging to work through because of the intensity of the alteration. The green rock environment has the opposite problem to the lithocap environment. Lithocaps are very profoundly altered. The distal green rock environment is barely altered. It's very subtle and subdued alteration. So the patterns you're seeing here from the central pink intrusion of porphyry is going from the stippled potassic zone through various sub-facies of propylitic alteration. And the alteration in the propylitic domains is zoned based on temperature. So close to an intrusion, if you're lucky, you might see actinolite, and it's forming above 350 degrees. It will be occurring with epidote, chloride and calcite, other components of the propylitic halo. And you can map the outer limit of actinolite, and it's basically giving you a high temperature near-miss indication of proximity to the porphyry. But many people are not very good at picking up that actinolite, or it's simply not present. So not many people have mapped actinolite domains around porphyries, but they can be found. We then have an extensive domain where epidote is the characteristic and diagnostic mineral, and in the green rock environment, it's the most obvious mineral because of its bright pistachio green colour. So we can map that epidote subzone really easily, and we'll see it in veins and we'll see it in altered rocks, and we may see it transitions from an intense vein stockwork close to the deposit out to just peripheral partial replacements of plagioclase and hornblende by epidote in the whole rock. So just mapping epidote veins can also provide you with a vector towards the deposit centre. So you can just do geology to work out where you are in the propylitic zone. Outboard of where epidote is present, and epidote's probably stable down to about 280 degrees. Then we go to lower temperature conditions and we get minerals such as chlorite, calcite. If we're in basalts, we will see prehnite, we'll see zeolites, and we're scratching our heads and going, is this related to a porphyry? Is this diagenesis? Is this seafloor alteration? Is this metamorphism? We just don't know. But the mineral chemistry can actually give you tools that tell you are in a system. Now, Paul Agnew from Rio Tinto has taken this cartoon and tried to explain to his powers that be as to why they are quite interested in green rock exploration tools, because they believe it's helping to explore undercover, and particularly with deposits that are under partial cover. So if we say the green rock zone's going out 6 kilometres or more from this porphyry centre, the porphyry system is older and eroded down. And so if we're looking in 3D, we're looking for that little finger of mineralisation and alteration around the intrusive complex, but it's buried under post-mineral cover, but not completely. Out 2 to 6 kilometres away from that porphyry centre, we've actually got outcropping propylitic alteration in the distant mountain range. Can we use that to find this deposit? So we're going to come back to this question late in the talk. We're going to talk a little bit about the resolution porphyry copper molybdenum deposit, and I'll show you this exact geological scenario, and we'll see if we can actually detect that very distal signature of resolution out in the surrounding mountain range. So our team has been working on Myra Global Footprints Research Project since 2004. There's been 5 iterations of the Myra industry-funded project, and we're just putting in place the next phase, which will start in 2022. And it's been a long, slow slog, basically looking at a range of different alteration minerals that occur in green rock and lithocap environments, doing the proof of concept that we can actually see the chemical footprint of these deposits in distal locations. The enabling technology is laser ablation ICPMS that allows us to get to low detection limits for various trace elements, and that's been really critical for picking up subtle signs of mineralisation in distal locations. The outcome of this is that you can add mineral chemistry to the explorer's toolbox, and with a very broad open sampling program, you can get indications both of fertility and vectoring. So fertility questions or prospectivity, does this district contain a significant system? Is there a potential for a discovery of a significant mineral resource? And vectoring, which way do we go and how far away are we from the centre? So I'll try to show you how you can do both of these in the green rock environment. So just to explain the basic concept of what we were trying to do, this is an example from the Baguio district in the Philippines. We published this back in 2014. The Baguio district is famous for its intermediate sulfidation epithermal veins, but it also contains a series of porphyry copper gold deposits. And we are looking at a rock that is distal to two porphyry copper gold deposits in the district. It is a lamprophyrdite, so it's hornblende ferric. It's only about 3 million years old, and those hornblends are as fresh as a daisy. And you can see this little epidote vein cutting through the middle of this sample. So from a geochemical exploration point of view, if we were doing a bulk rock analysis, basically we can break this into a useless rock and a useful rock because all the geochemical signature is preserved in the vein. There's very little hydrothermal alteration of the surrounding rock. And so if we just took a bulk sample, the chances of us picking up the geochemical anomalism from a bulk analysis is really tough because we've got significant dilution. So let's zoom in and look at that epidote vein here, and we see it's actually an epidote calcite vein. This is a reflected light photo. You can see the epidote is cutting the hornblende, and we can still see the primary cleavages in the hornblende. There's no real alteration of the hornblende, and we can see the calcite with the epidote. There are 3 holes at some laser ablation spots. And if we zoom in and do a laser ablation map to look at the trace element deportment in the epidote relative to other minerals, we can see that distal pathfinder elements such as arsenic, antimony and lead are actually in the epidote crystal structure. Epidote is taking up these distal elements that we use in mineral exploration. So we are always looking for distal arsenic, antimony and lead halos around porphyry deposits. And people tend to assume they're in the sulfides, but in the distal region where sulfides aren't present, they wind up in a silicate. They wind up in an epidote. And it turns out that copper and zinc go into chlorite. So here's a little cross-section through the centre of the Baguio district, or a map and a cross-section. We've got 3 systems. The Mexico prospect is a failed skarn and diorite porphyry complex that was drilled and had no significant mineralisation, but some anomalous rock chips. And the yellow domain around Mexico on the left here is the pyrite halo that's mapped at surface. We then have the Black Mountain porphyry copper gold deposit. It's about 35 million tonnes at about 0.3 copper and gold. And there are 2 porphyry centres giving us this elongate potassic zone in brown and pyrite halo. And then Anglo-American discovered the Nugget Hill prospect in 2000, and it has significant high-grade stockwork boulders that have been shed off of it due to a landslide after an earthquake and a typhoon. But the prospect hasn't been drilled because it's on the Philippine Military Academy grounds. And so permitting hasn't been permitted, but it looks like a really strongly endowed high-grade porphyry. We did sampling transects A, B and BC to look at epidote versus rock chemistry. And what you're looking at is a pseudo section on the right that shows you from Mexico to Black Mountain to Nugget Hill. And it compares rock chips to epidote mineral chemistry. The rock chips are in red. The epidote is blue triangles, and the filled blue triangles are vein epidote. The open blue triangles are replacement epidote, and the skarn epidote is a brown square. What you can see here is that the strong geochemical anomalism in Epidote is around the Nugget Hill porphyry. And we're picking up arsenic contents in Epidote up to 200 parts per million, a good kilometre or two out from Nugget Hill. And the rock chip samples from the same material are giving us arsenic values of less than 5 ppm. So we're really struggling to see geochemical anomalism outside of the pyrite halo to Nugget Hill using rock chip, but we're getting a very strong response in Epidote. And we're not getting that same response around Mexico. So not only are we seeing we're extending the geochemical footprint here using Epidote, we're also getting signs of fertility. The more fertile system is pumping out more metals, and we're seeing that anomalism in the surrounding halo. And so we've sat and thought about this, and we think what's going on is there is co-precipitation of different mineral phases occurring in different geochemical domains around porphyry deposits, and they are reflected in the alteration mineralogy. So in the core of a porphyry deposit, what is happening is we are stripping calcium from the rock because plagioclase is altering to K-feldspar, hornblende is altering to biotite plus magnetite, and so potassium is being dropped out, calcium is being mobilised, magnesium is being mobilised, sodium is being mobilised, and it's migrating. And we tend to think about fluid migration in porphyries going upwards, but it's also going laterally outwards. That's why the metal zoning patterns are zoned the way they are around the intrusion. There is lateral outflow taking place here. And so we move calcium outwards, we're depleting the fluids of copper, and so we go from chalcopyrite to a pyrite zone. This is our sulfide zonation. We wind up with a geochemical domain where we're getting epidote plus pyrite. Close to a porphyry, the epidote has really low distal pathfinder elements, arsenic, antimony and lead, and that's because they're scavenged by the sulfide phases. They go into pyrite or they form their own sulfides like galena and arsenic-bearing phases. Then we come to a domain where we actually run out of hydrogen sulfide, but we've still got metals in the fluid. This was a surprising thing about this work, is that the metals keep going, and once they don't have sulfur to bond with, they go into silicates. So we actually get our strongest geochemical anomalism of distal pathfinder elements in the silicates outside of the pyrite halo. And that's why we can extend the geochemical footprint beyond the porphyry centre. And an added bonus of this, and we've now worked on more than 60 porphyry deposits checking this out, is that the biggest ones flux the most metals. So the most strongly anomalous green rock minerals tend to come from systems that are giant porphyry deposits. They flux out a huge amount of pathfinder elements. So that's where we can get signs of fertility, strong geochemical anomalism in the distal green rock minerals. So epidote was our first mineral we worked on. We then moved on to chlorite, and we thought chlorite would be a horrible thing to work on, but it turned out to be quite amazing. And it surprises in that it's really effective at helping to detect where a deposit is within about 2 kilometres of the deposit centre. Okay, so it's the most extensive mineral in the district, but when you get close, it really provides some useful guides for exploration. This is the Batu Hijau district. We looked at the Google Earth image earlier. Now we're looking at Steve Garwin's alteration map. So the core of Batu Hijau has biotite magnetite alteration, and then we go out to distal propylitic alteration, intense epidote chlorite going through to weak chlorite. And the sampling transect you can see to the southwest going 5 kilometres out from Batu Hijau. These samples were collected by Zhaoshan Chang in very tough conditions. So he provided an amazing sample suite that's been really a boon to this research. And what we found in these homogeneous basaltic andesitic rocks is that there's a strong anomalism in chlorite that is allowing us to detect the location of the deposit. Basically, you get high titanium in chlorite close to a porphyry centre, so titanium is substituting in as a function of temperature, and the titanium content decreases markedly as you move away from the deposit. There are other elements such as strontium and lithium that are enriched in chlorite distal to the deposit. So if you ratio titanium to those distal elements for chlorite, such as a titanium-strontium ratio, you amplify the signal-to-noise ratio, and you get some significant trends. And what you're looking at in the graph on the right is the titanium-strontium ratio for that southwest trend. You can see it changing over 4 orders of magnitude out to about 2 kilometres from the deposit centre. And it's so systematic, you can actually work out distance to deposit. The black line you see here, that's the bulk rock composition. So if we did the whole rock analysis, we can't see this variation. But if we analyse the chlorite, we can see this gradient, and we can actually come up with a fit equation to predict distance to the deposit centre based on the trace elements in chlorite, such as titanium, strontium. We call this a proximity ratio, and I will show you how that's applied in a few minutes with another example. One of the things about mineral chemistry data is it's highly variable in nature. And so this is still the Batu Hijau data set. Now we're looking at a different mineral. We're looking at calcite, and we're looking at lanthanum in calcite, and we can see Batu Hijau and Sekongkang and Nangka and Bamboo. These are other prospects in the district. And you'd look at this and say, oh, lanthanum in calcite shows where these deposits are located. But the geochemical footprint from whole rock gives you a much bigger footprint. So, lanthanum in calcite is not useful. Well, if we take that southwest transect and we look at the laser ablation data, what we see is actually we get both highs and lows in lanthanum in calcite. There's over 6 orders of variability in the lanthanum concentration of calcite crystals in these rocks, which relates to hydrothermal processes. Sometimes it's just hot water precipitating out calcite with no lanthanum in it, and sometimes we're getting really enriched lanthanum in the deposit centre. So mineral chemistry data is highly variable in its nature. And again, if we compare to the whole rock, we can see we don't see that variability in the bulk rock sample. It's in the individual spot analyses. But what I'd contend to you is the variance in the calcite data is actually showing you also an exploration vector here, that the variability in calcite compositions is increasing from about 3.5 kilometres into the deposit centre, and highly variable mineral chemistry compositions are actually typical of the deposit centre. So if you believe that, maybe you can extend that calcite footprint out beyond 3.5 kilometres. The trick is you need to sample to background to see the anomalies. Calcite's an interesting mineral because if you use it in exploration, well, the most logical place to apply it is actually in carbonate-hosted porphyry systems where we don't have epidote and chloride. We get green rocks in volcanic and intrusive environments. In carbonate terrains, we don't get a lot of epidote and chloride. So here's the Grasberg deposit in Indonesia, and Jen Thompson, who's online and is now living in Denver, just finishing her PhD, has been working on these calcite samples on this transect down the Meron Valley away from Grasberg. And the beautiful thing about calcite is not only can you do mineral chemistry, but you can also do UV fluorescence and you can do stable isotopes. And so you can combine all of these techniques to try to take something that looks pretty useless, like these calcite veins in this distal sample of limestone around the Grasberg deposit, look at the fluorescence response, look at the isotopic signatures, look at the trace element chemistry in the calcite, and put them all together, and you can actually get several factors from the individual minerals that are all giving you confidence that you are getting proximal to a large porphyry copper system, such as this little summary cartoon that Jen's put together here. So hopefully Jen's paper on this will be coming out in Economic Geology sometime soon. It's still going through the review process, but Jen is in Denver, and I'm sure if you ask her, she might come out and give you a talk about the details of this. Going back to the green rock environment, we like to put epidote and chlorite data together. So here's an example from a place called Tools-Taldy in Kyrgyzstan, where we have a very broad sample grid. The 2 little pattern maps down the bottom are showing you our sample distribution. We were asking for samples about 1 every 300 to 500 metres and gridding them out. What we're getting is a coincident arsenic low and titanium, strontium and chlorite high. So the arsenic in epidote is low where the titanium, strontium is chloride is high. And that's basically the location of the Tools-Taldy porphyry copper gold deposit. So that's sort of giving you the idea of what we're hoping is the sort of sample distribution you can achieve to look for these deposits with the aid of this technique. What I want to show you now is a bit more detail on what you can do with epidote and chloride. And we're going to look at resolution in Arizona, because this is now going back to this question of concealed porphyry deposits. The resolution deposit is a giant high-grade system, 1.6 billion tonnes at 1.47 copper and 0.03 moly. It is covered beneath tertiary volcanics. It's laramide in age. So the photo we're looking at here, we can see the tertiary volcanics defining the ridgeline and overlying Proterozoic and Paleozoic rocks. So we've got Proterozoic sediments and volcanics and Paleozoic limestones covered by tertiary volcanics. So we don't see any geological expression of the laramide-age porphyry or its laramide-aged volcanic host rocks at surface in this district. Carl Henke put out a nice little image of the Superior District back in 2012, and we were looking basically at this ridge face, the range front here, where these epithermal veins are cropping out. You can see the Apache Leap is the tertiary volcanics, and the location of resolution is this red dashed line underneath the tertiary volcanics at significant depth. Town of Superior in the foreground, the magma veins shown over here on the to the north of resolution as well. So just showing you a geologic map. The tertiary volcanics are obscuring the eastern side of this map. You can see the resolution ore shell. You can see cross-section AB. You can also see the range front geology with the Proterozoic and the Paleozoic rocks. And you can see the samples that Rio Tinto sent to us to test the green rock technique. So we've published this in a paper in Economic Geology last year, just going through what we did with these 12 rock samples that they sent to us in what we call a blind site test. So the idea is send us your epidote and chlorite, don't tell us where it's from. Let's look at the rocks, apply mineral chemistry and try to work out if we've got a porphyry nearby, if it's large and how far away is it. So the rock samples they sent to us all have epidote and chlorite alteration. They look like this, very sparse epidote veining. Only one sample had an epidote vein, but they all had epidote replacements and chlorite replacements. When we did the epidote analysis, we found a subdued epidote signature. So here's a plot of arsenic versus antimony for epidote, and it's showing you our database. So it's showing you the range in arsenic and antimony contents we see in porphyry deposits. The blue circles show you metamorphic epidotes. So if you get epidote from metamorphic environments, it typically has very low arsenic and antimony. The antimony is often below detection limit, so it plots down in the bottom left corner. Porphyry-related epidote has detectable arsenic and antimony, and the further away you are from a big porphyry deposit, the higher the arsenic antimony signature. So the really big systems have distal epidotes that plot up in the right of this diagram. And they have proximal epidotes that plot down in the lower corner of this diagram. Small porphyry deposits also have proximal epidotes that plot in the low corner of the diagram, but the distal epidotes plot in the middle. And the resolution epidotes all plot in the middle. So it means either we're distal to a small porphyry centre or we're proximal to a large porphyry centre. You can't sort it out, but that's the sort of fertility indications we're looking for in our epidote data. And if we look at the rocks and we look at the epidotes themselves, we can see, yes, they contain arsenic, antimony and lead, but their contents are low and they coexist with pyrite, which is also containing elevated arsenic, antimony and lead. So this story about co-precipitation of mineral phases can explain why your geochemical anomalism isn't as strong in the proximal sample. So we think these are proximal samples. So that means chlorite should work. So here's our samples in a little map section, projecting them onto a pseudo cross-section. And we're now going back to the titanium-strontium ratio in chlorite. And we can see it vary systematically with depth through this cross-section. We're getting higher titanium-strontium ratios at depth. And if we use that Batu Hijau proximeter equation to calculate distance to the deposit centre, on a cross-section, it's going to plot up as a circle. In 3 dimensions, it's going to be a sphere. So that was the prediction of distance to where the heat source for this deposit would be from that top right sample. And if we do that for each of the 10 chlorite samples we could get data from, you can see actually these all converge and give us a target between the 2 sample clusters at considerable depth. And when you look at the ultimate response, which we didn't know at the time we did the work, you can see that actually we're sitting below the ore shell in between the 2 clusters, but you would have drilled through the ore shell to hit that target. So Rio Tinto were very pleased with these results. 10 samples on the 2K section, basically telling them, yes, there is a big system nearby and where to put the drill hole from chlorite mineral chemistry. But one of the things here is that this was an optimised section. It passed directly over the deposit, so the thermal anomaly associated with the intrusive complex was maximised. If we'd been tangential to the deposit, we would have got a more subdued and difficult to interpret signature. So Rio Tinto went back and checked the work. They have their own laser lab. They took additional samples, that's the ore shell, and they dealt with this in the 3-dimensional pattern. So they took these samples here from outside the ore zone, calculated distance to centre as a sphere rather than as a circle, and looked at where all the spheres coalesced, and again, they coalesced in the centre of the deposit. So this was checked twice and the results worked twice. So chlorite was a really effective vectoring tool at resolution. Epidote was a subdued response and gave us that ambiguous question, are we close to a big system or are we far from a small system? We knew that in the resolution district, if we go out to the range front, in the Proterozoic rocks, there's a lot of green rock alteration. Okay, so these are some of the dolerites and the basalts of Proterozoic age that are exposed in the range front all the way, 4, 6, 8, 10 kilometres away from resolution. These green and sort of pinky orange rocks through here are volcanics and dolerite sills. So we decided, let's go back and try to see if we can extend the geochemical footprint of resolution and work in the range front to see how far out we can detect resolution's footprint using chloride epidote chemistry. So this is Josh Phillips's PhD study that's just been coming out of confidentiality. And Josh wandered up and down the range front. So you can see here sample distribution of materially collected at surface and different alteration mineral assemblages. We even picked up a very interesting magnetite skarn a long way from resolution. And you can see epidote, chloride, actinolite, orthoclase, albite. We're picking up all of these minerals through these Proterozoic rocks. We were targeting Proterozoic dolerite and basalt because they were the favourable host rocks for the green rock. And we got a bit of a surprise here. What we were finding, and this is the Proterozoic basalt, is we could find amicdules filled with epidote, apatite, calcite, titanite. And so we thought, okay, here's a chance to do some dating, because if I just go back one, I should point out, in addition to resolution, there are other laramide intrusions. So there's the Silver King intrusive complex up here in the north of the district. So there we were thinking there's a potential for multiple mineral systems. Here we're seeing some apatite, maybe we can date it. And because epidote can contain uranium, let's look at the epidote trace element chemistry and look for samples that have the potential for dating. Epidote typically has a lot of common lead, but if we're lucky, sometimes you could date epidote using uranium lead if it's got sufficient radiogenic lead. And it turned out we could date these samples, or we could date a number of the epidotes as well as the apatites. And what this revealed was there is a Proterozoic green rock alteration event in the Superior District. And this alteration event wasn't known before. You can see on the left, we've got apatite and epidote dates, and they're rough, okay? They've got big errors on them with our different epidote dating techniques we've been developing at Codes. But even with those large errors, it's very clear these are Proterozoic events. And the fact that we're getting apatite and epidote showing the same events gives us confidence that this is real. The second sample you can see here, again, apatite and epidote giving us Proterozoic ages. On the right here, we're getting titanite and epidote giving us laramide ages. So we found that the green rocks in the range front were more complicated than we expected. We had more than one green rock event separated by over 1 billion years. That wasn't what we were thinking would happen. But what it meant is we could now do our mineral chemistry work, which had been proving challenging, and it was proving challenging because of this complicated overprint story. We could generate training data sets with constrained known ages of epidote chloride alteration and come up using discriminant projection analysis with screening tools that let us work out the different types of epidote chloride in the district, the different ages that allowed us to eventually establish what the distal footprint to resolution was. So a lot of our work at the moment that's going on in our Amara projects is going into multivariate element space, and adding in the capacity to date the alteration around the deposits really lets you pull apart the different alteration types and sort out what is porphyry related and what is background alteration. So this is some of what Josh was doing to come up with this porphyry signature. And surprisingly, what we could see is in individual grains, once we've done this work, we actually see a history of epidote growth over 1 billion years with late rinds in some samples, these ones down here with the high lead, strontium, zinc and copper rinds. That's the laramide epidote overgrowing cores of Proterozoic epidote. So we're getting inheritance of epidote, like we see with inheritance of zircon, which was really quite a surprise. And so being able to put all that together, here's actually now what we think is the chlorite zonation. This is a vanadium cobalt proximity ratio, showing that we can pick up the signature of resolution out to 4 to 6 kilometres away from the deposit in the range front, but we could only do that after we'd screened the samples. So these ancient terrains have complications that there may be multiple alteration events, but if you can combine epidote dating with the mineral chemistry, you have a really powerful exploration screening tool to let you work out the good from the bad. So that's it, folks. Just to wrap up, I think hopefully I've shown you that these distal alteration minerals are giving us geochemical footprints. They're providing us with vectoring and fertility information, but they're also giving us screening tools and we can date them. So they are very useful tools to add to the explorer's toolbox. Hasn't contributed to a discovery as yet. And so when these tools are part of a successful new porphyry discovery, I think it'll really give validation. But I would just like to say thank you to the research team over the years. There's been a huge cohort of academics, postdocs and students at Codes, at Lakehead University, Imperial College, and even at Colorado School of Mines. Jeff Edenquist was part of the original team when he was an adjunct at CSM. And so I thank them all, and I thank all of our sponsors over the years who've been providing the funding to really develop this, this research initiative. So I'm very happy to take any questions, and thank you all for listening.
All right, well, that's absolutely fantastic. Thank you, David. So we'll go ahead and open it up to questions. If you want to just unmute yourself, or if you want to type it in the chat, I can read it for you in a minute, but go ahead if you have any questions. Well, I have one while everyone's thinking. So I'm just wondering, how does the host rock environment influence the lithogeochemistry you're seeing in all of the minerals that you have discussed?
Okay, so good news is the fluid wins most of the time. So when I showed you the graph of epidote from the Philippines and compared vein to replacement epidote, we do that routinely when both veins are present and we're analysing wall rock replacement. We're always analysing the things that are actually in the crack where the fluid is dominant, and in the altered rock where we're getting that potential protolith contamination. And what happens is the metals of interest are being added from the hydrothermal fluid. So things like arsenic and antimony are not being inherited from a basalt or a rhyolite. They're actually extraneous to the protolith, so they're being added. Some elements, so like nickel, chromium, these elements in basalts, maybe you start seeing a bit of a protolith effect in the chlorite. So you do have to look at it, and you can take the protoliths into consideration if you know what your protolith geology is, and you can try to normalise your data to the protolith. But for most trace elements we've found, it's not a problem.
Very cool. Thank you.
I have a question.
Sure.
This is Larry. Yeah, Larry James. What if your host rock way out there is really low on elements compared to the ones you've been talking about in the green rock environment, really low on the elements required to make epidote or chlorite? Or it's very refractory, let's say, it just doesn't easily react with a low temperature fluid.
Yeah.
Do you still get a green rock environment in that, or a green rock trace element environment?
So Larry, that protolith is important. Epidote and chlorite need iron, and iron's not a soluble component, so they tend to form in rocks that have iron. So iron is a component you are going to inherit from the protolith. So if we were in a quartz sandstone, we're not going to make epidote and chlorite, we're going to make quartz. In a pure limestone, you're going to make calcite. And that's why you have to modify the approach depending on what type of protoliths you're dealing with. Many of the porphyry deposits that have been found are hosted in volcanic or intrusive rocks in total or in part. And actually our alteration models for porphyry systems are driven by those deposits. But when we go to non-reactive rocks such as quartz sandstones or highly reactive rocks such as carbonates, we need different alteration zonation models because they don't behave the same way. The propylitic alteration isn't propylitic. In quartz sandstones, it's actually silicic alteration, and it goes out 3 kilometres, and you have to analyse the quartz. There's nothing else there to analyse, and we've done that. Similarly with the limestones, well, Larry Minor and Zhao Shan do a great job of showing you about the manganese-coated cracks that you use for geochemical exploration. You can add in the calcite veins, but there's not a lot else we've been able to find in limestone terrains that can help you because the rocks are too reactive and they actually suppress the geochemical anomalism. You need structures that allow the fluids to get out a long way. And so, you know, basically your focus there is on veins rather than on pervasive alteration. I don't know, does that answer your question enough, or? You're muted, Larry.
What I brought up this question in a way, I used to do a lot of work around Bingham Canyon in Utah, and it's in a quartzite, a lot of it, and there's calcareous and magnesian, dolomitic units and some thin limestone beds that react beautifully, but the quartzite, if you walk around the place, you don't see much in it. And you take samples in the good old way of, well, how much lead and zinc and copper and the like are disseminated. It's remarkably close in. And I guess that's one reason is that no reactions easily occur in that quartzite.
Yeah, so Larry, we've worked on Bingham. We did a really extensive field campaign there. We went sampling all the way up Barney's Canyon, Melco, and south down into the gun clubs in the valley. So in that sampling, we did green rock work on the latite dikes because they extend for kilometres away from Bingham. And then we were sampling the limestones, the dolomites, and the quartzites. There is a beautiful halo in the quartzites around Bingham. And one of the things you look at is the texture of the quartz. It changes as you approach the deposit centre. It becomes more and more crystalline. So the quartzite per se is alteration. It's not metamorphic. And you can actually marry up the trace element contents of the quartz with the cathode luminescence response of the quartz. So I love quartzites as an exploration tool around porphyries. It also turns out that whole rock geochemistry works really well in quartzites. You don't need to use mineral chemistry so much because the trace elements are in the quartz. So analysing a quartzite, you're still picking up that trace element signature. But if you look at the textures of the quartz, they're changing systematically over 3 or more kilometres out from Bingham. But that requires detailed microscopic and SEM imaging.
Hey, well, thank you. I need a better hand lens, I guess.
Exactly. Well, get these students out there really pouring the high technology on to extend that what we can see, because it's hard to do with just the naked eye.
So we have a question in the chat just asking, what other minerals have you studied that are also useful for vectoring? So
in the green rock environment, we've been working primarily on epidote, chlorite, pyrite, tourmaline, calcite. In the lithocaps, we've been working on, well, alunite, Zhao Shan no doubt's told you a lot about, quartz, pyrite, weird minerals, like zunite, porphyryte. We're basically exploring the different minerals to see which ones of them are proving more or less effective. And they all have their own peculiarities about whether they're helpful. There's usually benefits that come out of each of them. And you have to adapt to what your system has. So if your alteration domain has a whole lot of actinolite in it, there's an opportunity to go chasing actinolite and look at its chemistry. And so you could potentially do that in skarns. I mean, this type of stuff has been done in the skarn world for many years. So it's just dragging the porphyries up to catch up to what people have been doing with garnet and pyroxene chemistry in skarns.
All right. Is there any other questions for David?
Speak the word skarn and he appears. Hello,
Yeah. Oh, okay.
Hi, Dave. Thanks for the fantastic, great talk.
Yeah, well, thank you for those great samples.
Yeah, we just started working on the carbonates around Bingham, and we also had Stephen working on Candelaria, the carbonates around Candelaria. Yeah, it's interesting to see the latinum you showed.
Yeah,
we see the latinum at one site, but not on at the other site, not at Candelaria.
Really?
Yeah.
So that is surprising.
Yeah. So I have been thinking whether the magma composition could affect those signatures. Obviously, Bingham, we know the composition of the intrusive rock. Bingham, Candelaria, we don't know yet.
Okay.
Uncertain. But
we're doing a fair bit of work up in the Cloncurry at the moment, Zaoshan, as part of the Northwest Queensland initiative. So we're trying to look at the various alteration minerals around some of the IOCGs there. And the rare earths are a really important part of that story. So maybe the lanthanum's going into a different mineral phase because the oxidized fluid should be moving around a bunch of the rare earths. And we're seeing strong anomalism, but I don't think we're seeing it in the calcite.
Yeah.
Yeah, but I have to go back and check. I can take a look and see, but that is interesting, Zaoshan.
Yeah, maybe we could talk about this more. So yeah, it reminds me that I did the combination of the skarns in China, and the zoning patterns, they really are affected by related to the magma combination, the redox state and fractionation, and whether if the magma combination is significantly different, normal calc alkaline versus alkalic kind of combination, if there's the LCG, a lot of LCGs are related to those very alkalic.
Yes, that's right, and we've got the alkalic porphyries as well. We could look. That's a good idea, Zaoshan. We should have a bit of a look at that and see.
Yeah. Different redox, different fractionation, and alkalinity.
Exactly. Yeah. Very good. We have a question in the chat from David. Could you see anomalous arsenic in epidote veins in the field with a portable XRF? So, David, I know that some of the industry sponsors of our research have gone down that path because obviously laser ablation is not a tool that the industry likes using. It's not an equipment that's available freely and easily through commercial labs. Some commercial labs are providing it as a service now. And so I know people have gone out and niche sampled epidote. They've basically broken open veins and scraped off to try to get a concentrate of epidote, use the portable XRF. And so the answer is yes. If the arsenic content is high enough, you will detect it with a portable XRF, but often you won't. But that's okay because it's the bigger systems that give you that arsenic anomaly. So that's what you want to find. So you could do a rough and ready early characterization and say, hey, we have got an arsenic anomaly here. So it's just like what Zaoshan would do out in a skarn, scraping all the manganese oxides off a crack and looking at that geochemistry. You can do that with epidote and distal, you're going to get that strong anomalism, arsenic, antimony, and lead. And the chlorite's going to give you copper and zinc. And they're all going to give you manganese, right? So the manganese halo around a porphyry deposit is contributed by the calcite and the epidote and the chlorite. So they'll all give you whether that manganese anomalism is there or not.
I guess you could use titanium also.
Yeah, that's right. Well, the portable XRF can be really helpful with titanium and possibly giving you better results than doing a 4-acid digest, especially if the titanium contents are high. So, yeah.
Thank you for that answer. And are there commercial labs in Australia doing laser ablation ICPMS?
So ALS are now offering the service, but they're sending the samples to our labs. So we've got 5 lasers and we do a bunch of commercial work along these lines. Imperial College are doing it as well. I don't know if they've got a partnership with a commercial lab, but yeah, I'm not aware of a commercial lab here that's actually bought their own gear.
Excellent. Thank you.
No worries.
So there's a couple more questions in the chat. We'll do these two and then let you go, David. But have you had any success with any other mineral than calcite in the carbonate host rock environment, such as late dolomite sediments?
So the late dolomite at Bingham is really interesting, and it has some very strong metal anomalism in it. But unfortunately for us, that's the only place in the systems we've worked on where we've had any significant dolomite alteration that we've looked at. But it teased us and made us think it would well be worth trying.
All right, last question. In your Batu Hijau map with the RTP mag, what is the alteration associated with the high mag?
So it's potassic alteration, and the Batu Hijau is associated with a sequence of tonalite intrusions placed in basaltic andesites. So these rocks are not particularly evolved, and so we get a lot of biotite and magnetite in the core. So there's an intense biotite, magnetite, plus or minus K-spar and albite alteration in the core, passing out to a moderate intensity biotite magnetite, and then passing out to actinolite epidote, which still contains magnetite. So the magnetite content of this system is increasing towards the deposit centre and getting really quite abundant. Not as abundant at Grasberg. At Grasberg, the core of that deposit has up to 10 volume % magnetite, and so its magnetic anomaly is even stronger than Batu Hijau's. It's just if you are at that erosion level and you don't have that overprinting pyritic clay-rich alteration destroying the magnetite signal, yeah, you can get a beautiful mag bullseye like we see at Batu Hijau.
Very cool. All right. Well, I'm going to go ahead and stop the recording here and thank